things that we're going to accomplish today. One of those things is going to be that we're going to finish our discussion of fundamental theorem part 1, and that will include any homework questions that you might have. Kevin? Philip? Where are you supposed to be?
Up front.
And the second thing that we're going to accomplish today is we're going to talk about fundamental theorem part 2, which is actually one of the most exciting parts of calculus that I... Yes.
How is it exciting?
How is it exciting?
Is there a song? Because if there's a song,
Yeah.
That would be cool. I should do a fundamental theorem song.
You should just do a music video.
Because if it's the most exciting, it should be hard.
It'd be like the most viewed video on YouTube.
The functions are alive with the sound of derivatives.
We gotta do a music video for photography. I might have to do that. That would be my
And then
guy.
have some like dancing division signs and dancing multiplication signs, and then they're just like in the back.
Philip.
yeah.
Except for anything. Oh wait, no, he's not.
Okay. So,
We didn't get the
yesterday we began our discussion of the fundamental theorem part 1, which is fairly impressive. It says that the derivative of an area function
19.
is simply the height of the curve. And this is our final derivative rule for the year.
We're learning nothing else in calculus here.
It was our final derivative rule. Nice try, though.
Um,
And so at the end of class yesterday, I started to do some more complicated examples that involve chain rule. And I'd like to do a couple of those examples at this time. For example, suppose I have something that looks kind of ugly like this right here. And so I'm going to think of, since I'm being asked to take the derivative with respect to x of a function of x cubed, I'm going to think of this as my inside function. And I'm going to think of the entire thing as my outside function. So I'm going to follow the form that I have here and do derivative of the outside, which gives me the cosine of x cubed squared. That is the cosine of t squared when t is x cubed, times the derivative of the inside function, just like so. Just like that. You can sit back next to Gloria. It's called shuffling the deck chairs. Now, sometimes students will look at this and they'll be a little confused. So if you're feeling confused, now's a good time to stick up a hand and ask. Yeah.
Why do we use T and also X?
Great question.
Because that's what confuses me.
Yeah. Cosine of t squared is going to be some sort of squiggly function, right? Like that. And so my actual axes, like here, would be y and t. And then x is some point that I'm integrating out to. It's actually x cubed that I'm integrating out to, like that. And so that gives me all of the net signed area from, well, it's really from 3. So I better put 3 on here. From 3 out to x cubed is the area. And so I'm thinking of this as a function of x because as x changes, the amount of net signed area will change also. Does that help?
Yeah.
The other thing about your question that's really important is that the identity of this variable right here really doesn't matter. If this had been s instead, so that I had an s-axis right here, I would have the exact same curve, the exact same derivative rule, and I would have ended up with the exact same derivative right here. And so for that reason, this inside variable often goes by the name of a dummy variable, because its identity does not really matter. It's just sitting there like a ventriloquist dummy and saying d squared dt. So that's a fantastic question. When you look at this guy, you want to think of this as a function of x and not as a function of t. Because the integration happens out to x cubed here, regardless of the identity of the variable that we have. The t is integrated out of the equation. Okay? Any other questions? Okay, well, let's take a look at one more example before we get to the main show for today. What if I have something like this? And in the spirit of Delilah's question, I'm going to use a different variable just because. Okay. So what if I have something like this? Please notice what's different about this is that I'm now using a variable x for my lower limit of integration as well as for the upper. In the previous example, I picked a constant 3, bam, and I integrated out to x cubed. Now I'm doing something that's a little unusual. I'm taking my root y plus 1, not y minus 1, y plus 1. There it is, root y plus 1. And I am picking a point x, and I'm integrating from x all the way to x squared, so that I get this area right here as my area function. And as x changes, my x is going to move this way, and my x squared is going to move that way even more. You see it? So that I'm going to end up with a rate of change of area because of both boundaries moving. Does that make sense? So the question is, how do I handle that? Well, there's a couple of different ways that I could handle it, but I think the easiest way to visualize it is by taking and splitting my integral at some fixed point c that lives between x and x squared. So if I do that, if I take my f of x is equal to the integral from x to x squared root y plus 1 dy, and I split it at some fixed point c, just like that, now I have two different integrals that are either exactly in or almost in the fundamental theorem form. F prime of x is going to be the derivative of this whole thing and I can use the sum rule to apply to differentiate a term at a time. This guy right here, the first integral, is almost in the form of the fundamental theorem, except for one small thing, and that is that it has the constant as the upper limit, but it has the variable as the lower limit. My fundamental theorem requires the variable to be the upper limit and the constant to be the lower limit. So I can flip those, and when I flip, I take the opposite. And here, this guy is ready to go. This is a function of x squared, so I can think outside, inside. The derivative of the outside, using the fundamental theorem, is the square root of x squared plus 1. And the derivative of the inside, I'll evaluate in just a second. Yes, ma'am?
Do you have to show that again, the library?
Yeah, good. So if we go back to our fundamental theorem form, you can see that the derivative of the integral from a to x with respect to x, f of t dt with respect to x, this is the derivative with respect to x of the integral from x to c. So it's not in exactly the form that I need, so I use integral properties to make that happen. And so this gives me now negative derivative of, excuse me, and now I get negative f of x, and I'll clean that up just like so. And I get this guy right here. Now this was fairly complicated, and the key move was splitting it at x equals c. I'd like to come back and visualize this so that this isn't quite so complicated. So let's visualize this. Here's the way we want to do it. Go back to our picture. As x increases, I'm going to get a little bit of an increase in area because x is increasing. How much? Well, it's going to be the height, which is f of x squared, times the width right here, which is not dx, but it's dx squared. It's the amount that x squared is changing by, which is 2x dx, right? Derivative times dx. Okay? Meanwhile, here, I'm actually going to lose some area. Because x is increasing, it cuts into my region, and the result is that my area changes by a negative amount. How much? By the amount negative f of x times the amount dx. And my total change in area is these two added together. If I now take the total change in area and I divide it by dx to get a rate of change, then my dx's factor out and cancel, and what I get is 2x times f of x squared minus f of x, just like that. So what is the upshot of all this? The upshot of all this is this. If I have a variable expression as an upper limit of integration, then when I take the derivative of my area function, I will get a positive rate of change with respect to that upper limit of integration. I don't mean it's positive in number, but I'll treat it as positive, express it as positive value. And then I must subtract off any change that happens as a result of the lower limit of integration. Does that make sense? So that if I come back down here, this expression makes a whole lot more sense. This is the rate of change as a result of the upper limit changing minus the rate of change as a result of the lower limit changing. And with that logic, it becomes much easier to do these kinds of things. So I can do something kind of crazy like, what is the derivative of the integral from x squared to x cubed of sine t dt, or something ridiculous like this. Okay? So I'm going to think in terms of the rate of change of the upper limit, and that's going to give me derivative of the outside times the derivative of the inside, less the derivative of the outside times the derivative of the inside. And once you see how the pattern goes, then the actual derivative is not very difficult to solve. How are we doing? Okay. Now for the big show, which is the fundamental theorem part 2. I claim that if you integrate f prime from a to b, Let's get a picture for this. What we're talking about is taking a graph of f prime and adding up heights times dx from a to b. That the area under that curve is exactly equal to f of b minus f of a. In other words, an area can be evaluated using an antiderivative. That's my point. Now, to see why this is so, all that we need is fundamental theorem part 1. So let me do a quick proof, and then I'll show you how this actually works. Let's let f of x be an area function that adds up all of the area from a to x of f prime of t dt. Now notice that I switched out variables here, and that's okay because this is just my dummy variable. And I did that for clarity so that we understand that f of x is a legitimate function of x. So if I do a graph of f prime here, then I'm fixing a point A, and I'm integrating all the way out to the point x, just like that. Now, what I'd like to do is I'd like to find capital F prime. But using the fundamental theorem, capital F prime is really easy, because this is exactly in the form of my fundamental theorem, isn't it? With little f prime being the function that I'm integrating. So that when I take the derivative d dx, integral from a to x of f prime of t dt, I immediately get f prime of x. Fundamental theorem, bam. Now something remarkable happens, because I observe that big F prime and little f prime have the same derivative. And we already know that two functions that have the same derivative are the same function within a constant, of course. So therefore, we can immediately say that f of x has to equal little f plus the obligatory constant c. Now this is really profound. We could stop right here and be really impressed, because what this is telling me is that my area function is automatically an antiderivative for f prime. This is one way to find an antiderivative, is to add up from a to x. And that's kind of cool. But wait, there's more. Because I can find the value of c by plugging in some initial condition. I wonder, what initial condition could I possibly find here? Well, there's only one initial condition I know, and that is that if I integrate from a to a, I automatically get 0 for the area, right? So therefore, big F of a, which is the integral from a to a of f prime, is equal to 0, and so that must equal little f of a plus the constant c. And that being the case, my constant c has to be equal to negative little f of a. Well, what does this mean? This means that I have big F of x equals little f of x minus little f of a. In other words, the integral from a to x of f prime is equal to f of x minus f of a. And if I now pick any point B as my x, then the integral from a to b of f prime is equal to f of b minus f of a, and we are done. In other words, I can evaluate an area by finding an antiderivative. Now let's see how this works out in practice. This is mind-blowingly cool. So suppose I want to evaluate the integral from 0 to pi of sine x dx. Like this. Now, graphically, what we're talking about is finding the area of the first lobe in the first quadrant of the sine graph, the first half wave, right here. I want that area. And I can imagine a painful process of estimating with rectangles, blah, 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 right? Or I can appeal to the fundamental theorem, and I can say this. If I think of sine x as f prime, then what is the f that gives me sine x when I take its derivative? In other words, what is the antiderivative of sine x? Not quite cosine, negative cosine. So that should be negative cosine of pi minus negative cosine of 0. F of b minus f of a. And the cosine of pi, negative 1. And the cosine of 0, so that I get an area of exactly 2. That's pretty awesome. And all of a sudden, our ability to find areas expands greatly. Let's do some more. We did this one. I think we did this one right here as our very first introduction to integration, estimating. We did rectangles and left sums and right sums. So we got some estimates, and I computed this by super secret dark arts, and I think I made an arithmetic mistake the first time, and we wondered how do we do it. Well, actually, I just used the fundamental theorem. The integral from 1 to 3 of x squared dx should be equal to the antiderivative of x squared, which is 1/3 x cubed. That's right. And I'm going to introduce a notation here. I'm going to evaluate that from 1 to 3. And what this notation means is that I am plugging in 3, I am plugging in 1, and I am subtracting. And this is pronounced evaluated from 1 to 3. And this gives me 27 over 3 is 9, minus 1/3, which is 8 2/3, or 8.6667. And with just a little practice, you can do it in your head. That's pretty cool.
So this is the deep dark secret.
This is the deep dark secret, the fundamental theorem. And isn't it impressive?
And actually,
BC, before calculator, this was the preferred way of finding your areas because your only other alternative was rectangles. And the rectangles
So
were...
this is what your calculator does, or somewhat?
Your calculator actually does not. What it does is it does 100,000 rectangles left and right averaging.
But this is how we do it by hand.
But this is the most, if you can find an antiderivative, this is the most accurate and most efficient way of finding it. So if you're stuck on a desert island, fundamental theorem is your go-to. If you have calculator available to you, your calculator is probably more efficient for these. Because not every function has an antiderivative, right, that we can find. Every continuous function has an antiderivative. It's the integral from a to x of that function. But not everyone can we find a formula. Okay, let's do more. Good, that'll work. Okay, so we look at this and we think to ourselves, fundamental theorem. Can I find a function whose derivative is 1 over root 1 minus x squared? Yes. What is that function? Nope. Nope.
Sine over arc sine.
Arc sine, right. Inverse sine, that's right. Equals arc sine of x And now I'm going to evaluate that from 0 to 1/2. In other words, I'm going to get arc sine of 1/2 minus arc sine of 0. What is the arc sine of 1/2? What is the inverse sine of 1/2 without calculating? Yes, what is the arc sine of 1/2? 3? No.
Pi over 6.
How do you know?
If you could sine, sine,
You're in a circle.
pi over 6 in sine, you get
1/2. Right. The sine of pi over 6 is 1/2. We use the unit circle to find the arc sine of 1/2. It's a special angle. What about the arc sine of 0? The angle whose sine is 0. Right?
No. No.
Use unit circle, 2 pi, but in the first quadrant we would call that 0. Okay? Yeah. And so we get pi over 6. Now, this is really fascinating because the graph of 1 over root 1 minus x squared looks something like this, with vertical asymptotes at -1 and 1. And what I'm saying is that if I integrate from 0 to 1/2, the area that I get just so happens to be exactly pi over 6. Wow. That's pretty awesome. More. Let's do more. Go. Great. Break it up into 2 factors. 3 and 1/2. We know between the x factors. And then I can break this either 4 to 2 up to the third.
Yeah. Yeah. I'll give us a second.
It's 4 to the third to 1/2, whichever is easier to evaluate. Okay. Let's see. Kevin, go.
You want to say just answer or just
I want this process.
first of all I just did sine derivative
Good. What'd you get?
2 over 3x x 3 over 2
Good.
and then yeah.
All right. How do we pronounce that?
Evaluate,
Evaluated.
and then bottom is 0. And
That's from.
from 0 2, 4.
That's it. Evaluated from 0 to 4. Practice saying that. So you can, all of you practice saying that so you can say it smoothly. Math is a language. And you don't want to sound like one of those awkward geeky types who don't know how to pronounce the language right.
Are those the geeky types? Some ones that don't know how to say it right?
Those are the geeky types, the ones that don't know how to say it right. Yeah.
Okay.
They're the ones that say, they're the ones that say thingy all the time, and you do this to that, and then, yeah.
Put it there. Put it there. Lock it there.
The real smooth mathematicians know how to pronounce this as the integral from 0 to 4 of root x. Okay, and so what we get when we evaluate this is like so. Okay, now what? No. No. First of all, the easy one. What's 0 to the 3 halves? What's that?
0.
0. Yeah. So this is 0. Now, 4 to the 3 halves. How do we think about that? You people have...
16
no way. Let's...
4 to the... 4 power.
When you have a fractional exponent, you can break it up using your exponent rules. 3 halves is 3 times a half, right? So, I can think of it either as this or as this, whichever one is easier. I kind of like this one because the square root of 4 is 2, and 2 to the third is 8. But if you want to do it this way, this works too because 4 cubed is 64, and the square root of 64 is 8. And so I end up with 8 no matter what. Everybody needs to know how to deal with these fractional exponents, and it's very simple. Exponent properties. Either one. It's not mystical. You weren't the only one. All right, and so now I get 2/3 times 8, which is? No. That's 3 halves times 8. What's 16 over 3, yeah. If you want to do it as a decimal, oh, it wasn't 3 halves times, yeah, I hear what you're saying. If you want to do it as a decimal, you must give 4 places always. So if you said 5.33333, I'm okay with that. You say 5.3? No, that implies 5.3000, and that's wrong. Okay? All right. Good. Good. What time is it, Bellman?
Should be at 33.
33? Good. We've got time for some more. Go. Okay, Philip Park. What you got? How?
It should be ln 4 minus 1, which is ln 1 is a 0.
Okay. So give me the process though. What do I write here?
Ln x going to be 1.
There you go. There's one thing missing here. What's the proper antiderivative of 1 over x dx? Absolute value. That's right. The plus c is a really interesting issue too. I'll come back to that in just a second. Because you notice that I haven't done any plus c's for these. There's a reason for it. It's not that it would be wrong. It's just that it would be redundant. And I'll show you what I mean. Because I am integrating from 1 to 4, all of the x's in the interval 1 to 4 are positive values. Therefore, the absolute value of any of those x's is simply going to be x itself. And so what I get is ln 4 minus ln 1, and the natural log of 1 is 0. So I get ln 4, exactly as advertised. So that's very good. But now I want to come back and address the plus c question that you raised. What if I had said that this equals the natural log of the absolute value of x plus, I don't know, 6 from 1 to 4, something like that. Any constant whatsoever. Well, then I would get the natural log of 4 plus 6 minus the natural log of 6 plus 6. What do you observe? See, the 6's cancel because we're subtracting one 6 from another 6. And it could have been any c that I used there. So since the c's will always cancel out, why don't I just make my life easy and make c equal 0? Any c will do, so we'll pick the easiest one. C equals 0. But I want to address one more question, and that is, why is the absolute value necessary? So consider this integral right here. The integral from -4 to -1 of 1 over x dx. Now when I consider the absolute values, what I get is ln 1, the absolute value of -1 being 1, minus ln 4, and I get negative ln 4 as my result. This looks very, very similar to what we had above. Why did it happen? Let's take a look at the graph, not of ln, but of 1 over x. When I look at the graph of y equals 1 over x, of course I get the familiar hyperbola with a vertical asymptote at x equals 0. And when I examine the area from 1 to 4, which has a value of ln 4, and I examine the area from -4 to -1, these two regions are congruent to each other, so they have the same area, but this region is below the axis, so that its net signed area is negative ln 4, just like that. If I neglected the absolute values here, then I would get the natural log of -4, which is an imaginary number. Actually, it's complex. There it is. That would be a problem. So it's really important that you not neglect the absolute value signs on your antiderivative for 1 over x. Okay? Let's do one more. Go. Let's see. you got, Nicole?
Is it a tangent inverse?
Arctangent?
Artangent. And then evaluate from 0 to 1.
Uh-huh.
Then arctangent 0 minus
Other way.
1 arctangent 0.
Top minus bottom. The angle whose tangent is 1. Hint, if the tangent is 1, then the sine has to equal the cosine, and that's at pi over 4.
Yeah.
That's right. Minus nothing.
Pi over 4.
This is pretty cool, because my graph of y equals 1 over x squared, 1 plus x squared looks like this. And what I'm saying is that this area right here just so happens to be exactly pi over 4. See ya.